So we've talked about this before, but if I have a function of two variables, like I have f of x and y, we can say something like this. We can say z is equal to some function of x and y. And so I've got two input variables, or I could say two independent variables, and then I have one output variable. Or I could say I have one dependent variable. So x and y would be my independent variables, z would be my dependent variable. And we've done this already, so this is not new, right? We had something like this. This would be my y-axis, and then we would have an x-axis like this. And then for a given point that has an x-coordinate and a certain y-coordinate, we would have this point in the xy plane. That would be like the input to my function. And then our function was always some kind of surface that lived up above inside the 3D space. And to get your output, you would map from your input up to the surface, and then you would map over to the z-axis, and the z-axis was like the output value of your function, right? But this had a specific geometric interpretation. This could be mapped as a surface, like a two-dimensional surface in 3D space. That's how we were visualizing it. If we have a function of three variables, then we can't use the same way, we can't think about it the same way, we can't visualize it the same way. Because like if I have some function g, and g is a function of three input variables like x, y, and z, then I can't just make a surface in 3D space. Instead, for this kind of thing, this is going to be best described by a scalar field living in 3D space. Oh, not 3P space, 3D space. In 3D space. And so what I mean by a scalar field in 3D space is like this. If I have, again, I'm drawing 3D space for you. If you have a 3D space, so I'm using all three variables to describe a coordinate point in my space, the function takes on some value at every point in space, right? And that can change from one point to the next. You get a different function value. It's hard to describe and it's hard to draw. But like one idea that I have in my head about scalar fields is it's kind of like fog. You don't get a lot of fog in Midland, but if you ever go to like San Francisco or someplace there's like a really foggy area, if you think about like the density of the fog, that would be like a scalar field, right? So fog exists everywhere in the 3D space, at least if you're outside. And you can think of the density of the fog as like the value of your function, right? So some places the fog is more dense. You could think of that as being like a higher value of your scalar field. And in some places the fog isn't as dense. And you can think of that as being like a lower value in your scalar field. So one of the things we studied in chemical engineering was heat transfer. And the idea of heat transfer was, well, one of the many ideas, is like you could have some three-dimensional object, but if I were applying some kind of heat source over here, like if I had like an electrical heating element and I put it on the textbook over here, and I really think about it, this book exists in 3D space, so you could apply like a z-axis and an x-axis and a y-axis, and you could describe points inside of this object. Every single point in the object has a certain temperature, and so the temperature of each point inside the book would be a scalar field. temperature is a scalar. It's just a number that describes, the average kinetic energy of the molecules. But temperature is just a number, but it varies every point in the book. So that's what I would call a scalar field. Does that make sense? Temperature is a scalar field of this 3D space. Okay.
Is the same idea about space-time, or it's different?
I would say that's different. Space-time is kind of like a 4D space. You could talk about like mass density in 3D space, and that would be a scalar field. Like if you imagine that this textbook weren't all made of paper, but like you have some object where some regions are made out of a higher density metal and some regions are made out of a lower density metal and some regions are made out of plastic and so on. You could talk about mass density as being a scalar value in a three-dimensional object. So actually, one more example I can think of before we move on. I can pull up something on, and I'm going to do my best to explain what it is, but I have to find it first. Okay, so take a look. So maybe I've mentioned this before. Electrons, right? Or electrons. The hydrogen atom, if we start talking about the hydrogen atom has one proton in the middle of the atom in the nucleus. That's all the nucleus is just one proton particle. And then we talk about the single electron of hydrogen as orbiting the nucleus, right? And you've probably heard the term electron cloud before. So an electron is not so much like a little moon orbiting a planet. It's not like just going around in a circle. It's not just orbiting the proton in a circular path. But the electron sort of bounces around because it's a weird quantum mechanical object. And so what this picture is it's kind of like a picture of the hydrogen atom where the proton in the nucleus is right in the center, and then this picture is a picture of like what the electron cloud might look like. Where I have black, that's practically zero probability of finding that electron in the cloud. Where I have white, this intense area, that's like a really high probability of where you might find the electron if you were searching for the electron with some kind of detector. And then of course like purple and orange are like intermediate probabilities where you'll have a higher probability if it's orange and a lower probability if it's purple of finding the electron there when you go to search for it. But quantum mechanics is weird, and so you can't really pinpoint the exact location and velocity of an electron. It's just not possible. You can read about that online. But what we can do is we can use the equations that we know about to generate these sort of probability density diagrams, right? So we say at any given time, if you knew where the center of the atom was, then this is what the probability density of the electron is. But you know that hydrogen atoms are not two-dimensional, they're a three-dimensional object that lives in our three-dimensional world. So in a hydrogen atom, you've got this proton in the nucleus, and then you've got the electron shell all around it in 3D space. So this image right here is actually a trace. This image right here is if I took like XY plane trace of the electron density. So I'm doing my best to show you in 2 dimensions what this really is in 3 dimensions. And if you can imagine what this would be in 3 dimensions, like imagine rotating it, this would represent a scalar field, right? So we're talking about a 3-dimensional space where the scalar is the probability of finding the electron. So it would be a scalar field. Right? Okay. And electrons are kind of interesting because electrons can exist in different orbitals, right? Like they can have different energy levels, but they can only have discrete energy levels. They can't have like a continuous range of energy, but they live in discrete energy levels. And so depending on the energy of the electron in the hydrogen atom, you can get all sorts of crazy different scalar fields that describe, the probability density of finding an electron at a certain point in space around the nucleus of the hydrogen atom. And so you get all these shapes that get crazier and crazier as the energy levels go up.
Basically, like the scalar field tells us, like, if you input a point x, y, and z, gives you the probability at that point, quantity, which is a scalar.
Mm-hmm.
Yeah.
Exactly. Yeah. So you tell me the point x, y, and z, and I can tell you the scalar, the probability of finding an electron there. In fact, I made a poster. And so I made this poster after taking a class called Physical Chemistry 2. And this poster is hanging in my office, by the way. If you go by my office, you can see it on the wall. But I made this poster as a way to just summarize what I learned in Physical Chemistry 2, which was an interesting class. It was a class where they teach you about quantum mechanics, and then you use quantum mechanics to determine these scalar fields of the electron cloud for the hydrogen atom. And I normally show this to students whenever I try to explain that complex numbers are important, right? Because this, where is it? This right here, capital P, that is the probability density of finding the electron at a certain point in space. So what is P? P is the complex modulus of psi squared. Okay, so it's the absolute value of that complex number psi, and then you square it. So what is psi? Well, psi is this function. Notice, what is it a function of? It's a function of rho, theta, and phi. So if I said if you give me an xyz coordinate, but if you give me a certain rho, theta, and phi, where rho is the distance from the proton, theta would be, a direction around the xy plane, and then phi is the distance, or the angle from the North Pole. So if you give me these spherical coordinates, then I can tell you what psi is according to this equation. And there's some crazy functions baked in here. One of the crazy functions is this y function. That's called Laplace's spherical harmonic function. And if we zoom in to Laplace's spherical harmonic function, then you can see a little lowercase I. So that's an imaginary number, and so that's where the complex numbers come into in this. And all of quantum mechanics is really based on complex numbers, so that's why it's important to know. Anyways, I made this poster, and you can see that's the whole idea, is that you can generate a scalar field that describes the probability density. And so that is a few examples. You can think of it like temperature, you can think of it like fog, you can think of it like electron density. There's a lot of different scalar fields in our kind of everyday life. But it would be really difficult for me to draw a scalar field, right? We can try our best with colors and traces and stuff like that, but it's hard to draw like a four-dimensional object. Okay. So we can ask about domain and range for multivariable functions. Like in this, it's a function of two variables. So x and y are my input variables. The domain would be all real numbers x and y. And the range would be only, only positive numbers, right? Because whenever I ask about domain and range, I want you to only think about real numbers. So in this case, the range would be 0 or any positive number for the values of my function. I say this, and I repeat this all the time for my algebra students, but you guys probably already know. Domain is the set of all allowed inputs to your function. Range is the set of all possible outputs. I'll write that up here. So domain is set of all allowed inputs inputs. Range is the set of all possible outputs. Okay. 7. Now what about this one? This one, my domain is not all real numbers. For this one, I have to remember that the natural log, or any logarithm function, I can't plug in 0 and I can't plug in any negative number for the argument of the logarithm. So that means the domain is the set of all numbers x and y such that x times y is greater than 0. And practically speaking, if you have an xy plane, like this one, quadrant 1 would work, because all the values x and y are positive. And what other quadrant? 3, yeah. Quadrant 3 would also work, because x and y are negative, so x times y would be positive. So that means quadrants 2 and 4 don't belong to my domain, because those would give me a negative argument for my logarithm. Does the origin belong to my domain? No, so I can't include the origin either. Okay. Then for the range, what is the range of that function?
Negative infinity to plus infinity.
Yeah, it's all real numbers. Okay. Again, the next one is a function of 2 variables. So for my function here circled in purple, what is my domain?
X squared plus y squared should be greater than 9.
Yeah.
And x equal from 0.
Yeah. So since we're thinking of real numbers only, I can't take the square root of a negative number. So I need it to be the set of all values x and y such that x squared plus y squared is greater than or equal to 9. That way my square root ends up being 0 or positive. And so here, if I were going to draw my domain, I can draw my domain in an xy plane. What shape does my domain make?
The plane is doing the disk of radius 3.
Perfect. Yeah, so I can draw a little circle at the origin with radius 3. And then the domain would be everything in the plane not in the circle, right? Because the circle would include all the values x and y, where x squared plus y squared is less than 9. And so I don't want that. All right, what about the range? Yeah. The range can be all real numbers because I can at least get to all of the positive numbers if I set x equal to 1 and I let y sort of go all over the place, right? And then if I wanted the negative numbers, I could set x equal to -1 and then I can let y go all over the place. So that range is all real numbers. So next one.
So we don't worry about the domain restriction?
Are you talking about the purple one?
Yeah.
So over here, we said that my domain was only the x and y values that were outside of this circle with radius 3. And if x in the denominator were 0, you're right, that would break the function. But Oh, you're right. Yeah, you're right. So my domain also has to exclude the x-axis, no, the y-axis. Yeah, my domain of the purple function can't include the y-axis, because if x is equal to 0, I'd be dividing by 0. Yeah, that's a good point. Thank you for catching that. Yeah, so the y-axis is not in my domain. For the purple function. Because of can't divide by 0. Okay. And so you would also need to say such that x squared plus y squared is greater than or equal to 9, and x is not equal to 0. All right, this green function in green, my domain is going to be the set of all values for x and y such that x squared plus y squared is less than 9. Because my denominator, inside the radical, I should say my radicand can't be negative, and also my radicand can't be 0, because if it were 0, then I'd be dividing by 0. So I have to say x squared plus y squared less than 9. Now for my range, I believe my range is all real numbers again, because I can set I'm trying to make sure that's right. It's hard to think about, though. Is it all real numbers? So if I let x be any number, then that means the numerator could get to all real numbers, but then I would also have to change my denominator as I change x. So it's hard to say. Try to graph it. So .3D calculator. And we're going to graph z equals x divided by the square root of 9 minus x squared minus y squared. Okay. So it looks like that is, as the range, as the z value goes, it looks like it is going to reach all real numbers. Trying to think of a good explanation why, but oh well.
Y can be 0, and then 9 minus x squared can go to positive to infinity as x approaches 3.
Yeah. Yeah, it seems like on that circle, right? The circle of my domain, where it's just the disk of radius 3. As you get towards the boundary of the circle, then the values either go to positive infinity or negative infinity really rapidly. So the range is definitely all real numbers, and you get there just by going towards the edge of your domain. Yeah, okay, that's kind of cool. So let's look at these. Now I'm looking at functions of 3 variables. And so the domain here is going to be any coordinate triplet where x, y, and z can be any real number, right? Plug anything in and you'll get a real number output for that function. And the range is, as well, all real numbers. For this, the domain is kind of interesting. So the domain has to be the set of all triplets, x, y, and z, such that x times y times z is greater than 0. The range is, again, all real numbers, but this is kind of an interesting conversation too, because whenever we talk about the xy plane, we talk about quadrants. In the xy plane, we have these quadrants 1, 2, 3, and 4. But what about in 3D space, right? In 3D space, we have another axis. So how many little, well, almost gave it away. How many little sections of space are there if I divide it up with the axes and the planes?
8.
Yeah, if I've got 3 planes intersecting each other, that divides space into 8 different regions, right? And so we call them octants. And so this domain where x times y times z is greater than 0, that is describing 4 of the octants. There's 4 octants
All of them
where it doesn't work.
Positive, 2 of them negative, 1 positive.
Yeah. Yeah, and there's 4 octants where this domain in this scalar field exists, and there's 4 octants where you don't get a real number output from this function. Okay. Here, this one is pretty similar to one we did before. This time, the domain is going to be such that first of all, x can't be 0. Thanks to Stephen's insight a minute ago. And also the radicand has to be greater than or equal to 0. And so that means x squared plus y squared plus z squared has to be greater than or equal to 0. Or sorry, 25. And so the domain is going to be everywhere in 3D space except for the YZ plane, because that YZ plane is where x is equal to 0, and except for a sphere of radius 5. And whenever I say a sphere of radius 5, I'm actually misspeaking. What I mean is a ball of radius 5, because I'm talking about a 3-dimensional object where a sphere is referencing the 2D surface. How do I explain that? So if I have a beach ball and it's like full of air, right?
Okay.
If I have a beach ball, the plastic part is a sphere. All of the gas on the inside, all of the air on the inside is what we call a ball in math. And so, actually, if I was being really specific here, the sphere of radius 5 does belong to the domain because I have a greater than or equal to. So the sphere of radius 5 belongs to the domain, but on the inside where the air of the beach ball is, that does not belong to the domain. So I would say the sphere of radius 5 does belong to the domain, but the ball of radius 5 does not. So spheres are 2-dimensional surfaces that live in 3D space. Balls are 3-dimensional solids that live in 3D space. Yeah.
Okay. Could specify in terms of distance from the origin, such that the distance from the origin is greater than 5.
You could say rho is less than 5 is a set that's excluded from my domain. Yeah. Yeah. remember on one of my exams that I took in the fall from Texas Tech, the solution to the problem was I had to write the intersection of two balls with radius 1, which is like real math terminology, but it sounds kind of funny when you write it. Okay, and so then I think the range here is also going to be all real numbers.
Intersection of two balls radius 1. That means two full solids intersected?
So then here the domain is going to be restricted to just the ball with radius 4. So the domain is going to be such that x squared plus y squared plus z squared is less than 16. So the domain would just be the ball of radius 4 centered at the origin. And then the range would be all real numbers like we showed with the two-dimensional case.
So the range pretty much for all of these is always going to be all real numbers? Or
Yeah, well, except for that one, but yeah, no, you could definitely think of a case where the range is not all real numbers. Like, what if I gave you this function? It's a good question. So, like, what if this were your scalar field, right? If I had x squared plus y squared plus z squared, the range would only be 0 or positive numbers. Or I could give you this function. Right? So the exponential function has to be positive for real valued inputs. And so that would obviously just be the range from only the positive numbers, not including 0. And so there's different ways you can get different ranges. Like I said, including in those examples. So here, I want to remind you, if you see the phrase level curves in the textbook, I think I was referring to those a few weeks ago as level sets. So just know those are the same things. Level curves, level sets. It just means you have a curve in 2D space that describes the same z value or the same output value of a function of two variables. When we talked about topographical maps, how we use topographical maps to like map regions with mountains or canyons or valleys or interesting geography. But in a topographical map, you just have a whole bunch of level sets drawn together on the map so that each curve you see represents a constant altitude. And also if you see the word contour map is the same thing as topographical map. I found this online, and I thought it was interesting applications of a contour map, besides like a topographical map that shows altitude. I want to open this in a new tab. Here we go. So this is something you might see on like a weather report, but this is a contour map, or you could say this is a topographical map. Here, the level sets are the lines in between the different colors, right? So the line in between green and blue, that is a line that represents a certain temperature. Right? So between green and blue, that's a line that represents 30 degrees. And so everywhere on this boundary between green and blue, everywhere on that line, it's exactly 30 degrees Fahrenheit. Yeah. And the line between green and yellow is a place where it's exactly 50 degrees Fahrenheit. If you go to any of those locations exactly on the line, it's 50 degrees Fahrenheit. So again, temperature is kind of like a scalar field. This would be a two-dimensional space where temperature is a scalar, and so this is kind of like viewing a two-dimensional scalar field. You can also see these maps, and I didn't ever really think too much about this, but if you see these little lighter colored lines, those are level sets for atmospheric pressure. And so if you look where it says H, this is a region of high pressure, and all along this lighter colored curve, it's exactly the same atmospheric pressure. And so you can see as you cross the curves, then you're decreasing in atmospheric pressure until you get this region of low pressure over here, or this region of low pressure over here. But everywhere you go, as long as you're traveling along one of these paths, then you never, ever, ever change atmospheric pressure. As long as you travel along the curve. So the last topic is, what if you have a three-dimensional scalar field and the values of your scalar are changing continuously with any change in your, three-dimensional coordinates as you're moving around space. You can create the analog to these level curves or these level sets. And in this case, for a three-dimensional scalar field, it would be a surface, right? Like if we had a space heater in the corner of the classroom, we could parameterize this classroom and say this is the z-axis, this is the x-axis, and this is my y-axis. So at a given XYZ coordinate position in the classroom, you would measure a certain temperature, and as you got closer to the space heater, it would be warmer, so the temperatures, that scalar would be higher, and as you got farther away, the scalar would be smaller. But you could create a surface in the classroom that would represent a surface of constant temperature, right? That would be a level surface. So I've got another example. You remember these? Remember, this is my best attempt at visualizing the scalar field that describes electron probability densities. So I made another set of images, but this time these are level surfaces. Okay? So you remember how some of these looked earlier, where I was taking a trace and then I was using colors to represent intensity. Now imagine this is, again, describing the electron cloud around a proton in the nucleus of your hydrogen atom. So the nucleus is somewhere in here. What you're looking at is my best attempt at rendering a level surface. So at any point along the surface, you're experiencing the same probability density of electron. The scalar in that scalar field has the same value any place along this level surface. So inside this level surface, the probability densities are getting higher, and outside the surface, the probability densities are getting lower. But the way I created these surfaces is just setting that scalar field equal to a certain constant, and then it was pretty involved just plotting that.
So it just involve the surface, on the surface or inside? Does it count too?
Huh?
Inside the volume, inside.
No, so a level surface is a two-dimensional object. It's a two-dimensional surface. So it's not like a 3D solid. It's like a sphere. It's not like a ball. Anyways, let me try to do a side-by-side comparison. Let's pick a really pretty-looking one like 540. So if I took a slice of 540 and I was looking at this, and you imagine rotating it in your head, and so you can kind of picture what the three-dimensional scalar field would look like. But then let's try to imagine I pick a constant value, and I say I want to just make a surface at a specific constant value so that my scalar field is equal to that constant. So maybe I'm thinking the constant value I want is somewhere between the orange and the white. Right? So white is a greater value, orange is a smaller value. So my value I'm choosing is going to be the boundary between the orange and the white. Whatever that scalar is, that's going to be the surface I make. So now let me try to find 540 in here. If I took that boundary between the white and the orange and then I rotate it around in 3D space, then this is the surface This is the level surface that I would get. So again, anywhere on the surface represents the same scalar value in this 3D scalar field. So
you use the one you showed us on the poster to determine this?
yeah. Well, I had to write 2 separate Python scripts, one to generate the 2D images and one to generate the 3D images, because it's completely different calculations, but the same idea. Anyways, so if you wanted to create a 3D scalar field, that's just a function with 3 inputs and 1 output. But if you want to generate a level surface, what you do is you say, okay, I've got a function of 3 variables. I'm just going to set this equal to a constant, right? And so to generate a level surface, I could take, for example, x squared plus y squared plus z squared equal to 42. That's not nice. Equal to 49. And I would say that like my function is x squared plus y squared plus z squared. That's a function of 3 variables. If I just set that equal to a constant, now I have a surface. That surface is a sphere with radius 7. And so the sphere with radius 7 is a level surface of just this function, which is x squared plus y squared plus z squared, right? It said match these curves to the equations that describe them. So there I gave you 10 equations and I gave you 4 curves. And so you're just supposed to write the letters A, B, C, D in these blanks. Okay. So one thing we talked about in class is that there's a difference between closed curves and open curves. So this is a closed curve because as you go around the curve, you end up back where you started, right? It makes a closed loop. Over here, this is an open curve because if you keep following the helix, you never end up where you started. It's like an open rope. So closed curves are kind of like rubber bands, and this one ends up back where it started. And this, again, is an open curve. It's more like just a rope. It doesn't end up where it starts. It just keeps on going. So we've got 2 open curves. For these closed curves B and D, I know that that doesn't work because those are not periodic functions. That could be the case because it's periodic. That doesn't work because those aren't periodic. That's periodic. It could work. That's not. That's not. That could work. That's not. That's not. That's not. Right. So there's only 3 possibilities for answer choices B and D. It's either this one, or this one, because these are the only 3 that have only periodic functions. Now, sine of t, sine of t, sine of t, that's going to be a case where for a t value, all of your coordinates x, y, and z are the exact same. So that's actually going to make a little line segment between the point -1, -1, -1, and the point +1, +1. It would just be a straight line segment. So that doesn't appear. Here, cosine and sine for my x and my y variables tell me that I'm going to have a circle when I project it onto the xy plane. And then sine of 2t tells me that I should expect 2 places where the z value increases and decreases. And so this matches with here, where if you projected this curve onto the xy plane, you get a circle, but then as you trace around that circle, there's 2 places where the z value increases and decreases. Okay. Likewise, this one, cosine sine, tells me I've got a circle when I project it onto the xy plane, and there should be 5 places where the z value cycles up and down. And so this is hard to see, I'll give you that. That was a complaint, is that it's hard to tell that if you projected this curve onto the xy plane, you'd get a circle. But there are 5 places, 1, 2, 3, 4, 5, where the z value goes up and down as you're tracing a circle on the xy plane. For our 2 open curves then,
Oh, I see it now.
I noticed that the open curves A and C, they both have this circular pattern going on in the xy plane. In fact, I think A is pretty easy to identify if you've seen some of my examples that I used during lecture, because I use this a lot. This is just a helix, right? So I'm tracing a circle in the xy plane, and then as my parameter increases, I'm just going up at the same rate in the y direction. And so this is cosine sine t. That's the helix equation. So the last one that we haven't nailed down is c. Again, I see circles happening in the xy plane. I see I'm going up at a constant rate in the z direction. And so up in a constant rate in the z direction, I'm looking for one of these curves, like this one or this one or this one, where the z value is just t, because it seems to just be going up at a constant rate. But how do I get circles that are small here and small here, but they get bigger in between? And so this is the effect of having t times 1 minus t. Because when t is 0, then the x values and the y values are 0. And when t is 1, the x values and the y values are 1. But at like t equals half, in other words, like my z coordinate equals half, then these x values and y values are going to reach their greatest magnitude, right? And so here what we're seeing is at 0 and at 1, for my z coordinate, this spiral kind of shrinks to 0, goes to the z-axis. And then where z is half, that's whenever this sort of shape gets to be the largest magnitude. So I totally understand that this was a tough question, and maybe I should have given you only like 8 equations instead of 10 equations. But what I was hoping you would do is I was hoping you would sort of use those principles and your deductive reasoning skills to slowly, by process of elimination, eliminate the choices until you narrowed it down to 1.